In this work, we present an adaptive controller for the triadic collaboration between human, robot and functional electrical stimulation in gait rehabilitation. After years of development, robots can now reliably interact with humans to provide support during physical therapy. When this is combined with functional electrical stimulation, the induced muscle contractions may benefit the user from increased sensory feedback, calcium concentration in bones and other physiological benefits. However, this hybridization of robot and electrical stimulation needs to be addressed with care, to ensure that the level of assistance provided to the patient is appropriate. This is to prevent the rapid onset of muscle fatigue due to electrical stimulation, or the likelihood of the patient becoming overly reliant on external assistance. To this end, we have designed a hybrid adaptive controller for ambulatory patients, to provide assistance as needed, and prevent muscle fatigue. Based on the principles of path control, we implemented a hierarchical control structure, whereby the user's voluntary motion is the main driver of the system, and assistance is provided to help the patient follow the kinematic path that is right for them. This hierarchical structure is achieved by defining 3 regions around this reference path. The first one is the dead band region, where the user's movement can be free from any assistive forces. The second region is the electrical stimulation region, where assistance from electrical stimulation is provided. And the third one is the hybrid region, where assistance from both the electrical stimulation and the robot is provided. This control structure capitalizes on the active participation of the patient, and prioritizes assistive forces from electrical stimulation, before any assistance is provided from the robot. Now, to ensure that within each region the level of assistance provided to the patient reflects the needs of the patient, adaptive control was implemented. The aim of this adaptive control is to provide proportionately more assistance from the robot than the electrical stimulation as the level of muscle fatigue rises, and to also reduce assistance from both the robot and the electrical stimulation as the performance of the patient improves. To validate the controller's response, we carried out a pilot study with one healthy adult. We used musculoskeletal modeling to first validate the controller's response in simulation, before we validated it experimentally. In both cases, we observed that the hybrid adaptive path controller was able to reduce the overall assistive forces delivered to the user, while preserving the fitness of their muscles and their ability to accurately follow the desired kinematic path. These results are encouraging, and we hope to replicate them in a larger experimental study, with participants who experience gait abnormalities due to neurological disease or traumatic injury.